receptor ligand binding in the last lecture. So, what we looked at in the last lecture was a case of a receptor binding to a ligand. So, I talked about the receptor being on the cell surface, a part of it inside the cell surface, in the cytoplasm, a part of it outside the cytoplasm. The ligand comes and swims and binds to the receptor. So, then we looked at the kinetics of receptor ligand binding, and we looked at the simplest possible kinetics, which is the case of R receptor binding to the ligand directly, R plus L giving RL. So, and then we talked about free receptors and total number of receptors and free receptors and the complexes formed. So, today what we will do is we will look at other kinds of kinetics. So, this is a simplified kinetics that may or may not occur all the time, but in a realistic situation you can have other kinds of kinetics coming in. Before we do that, let us very quickly go through what we did in the last class, because I hurried a little bit towards the end of the lecture. So, this is the kinetics that we looked at, L plus R giving C complex, and then the complex will then that is what is required over here, and K1 and K minus 1 being the forward and the backward rate constants for the system. And this is how we wrote the kinetic equation, the basic balance equation for the complex. So, ddt of C equals the forward reaction K1 times Cr times Cl minus K minus 1 Cc, right, if you remember it right. Now, what we said that we do not want to express this in terms of concentration, we want to express this in terms of numbers. So, Nr being the number of receptors, Nc being the number of complexes. So, free receptors is Nr, Nc being the number of complexes, and Nrt is the total number of receptors, which includes both the complex and the free receptors, right. So, then we said that how do we convert these concentrations into numbers. So, ligand is obviously in a concentration because it is in the liquid form, but we found out a way of converting this to numbers, because the total amount of ligand Cl naught equals the amount of ligand that is present right now plus the amount of ligand that has reacted with the receptor to form the complex. So, that is given, the concentration of that is given by N times Nc over Na, N being the number of cells per unit volume. So, if Nc is the number of complexes per cell, then N is the number of cells per unit volume, then N times Nc would be the number of complexes per unit volume, right. That you divide by the Avogadro number to get the molar concentration of the complex that is formed, and so therefore, that so the Cl that you have, the concentration of the ligand is initial concentration minus this value, or in other words, initial concentration is current value plus whatever current free ligand plus whatever has formed complexes, correct. So, then we can substitute it back. So, now we can have this entire equation almost as in the form of a number, right. And then we said that we can go ahead and solve it. We can go ahead and solve this also. If you, as you can see over here, this is a second order equation in NC, and this could be solved using partial fractions. But we wanted our life a little simpler, and we made a simplifying assumption, which is that Cl naught is much larger than this. So, this could be taken as a constant, and it becomes a first order equation. So, we had this first order equation over here, and then Nc naught, we assumed Nc naught to be 0. So, we had the exponential part, and then we figured out how to evaluate the half time, and this is a plot and so on. So, I just want to do the last bit. Yes, I think this is where I was little fast. So, Nc is the so if Nc naught is 0, then you have the exponential variation, and we figured out how to evaluate these constants. Now, the thing that I want to talk about is this one, the last thing I did, which is a Skachert plot. So, Skachert plot is essentially a steady state diagram. So, for example, here when you are plotting this is your basic expression, the one in the box. Now, when you are plotting this over here, you are doing an unsteady state plot, right. But the Skachert plot is the steady state version of it. So, steady state means this expression with time going to infinity. So, the steady state would be Nc would be Nrt Cl naught over Kd plus Cl naught, and that is a very important number for us, or an important expression for us, because it is easy to measure, because it is always harder to measure dynamics of a process, because you have to keep measuring at every time instant, at every time interval, whereas for a steady state you can let it happen for as long as you want, and then you can measure it. So, so the steady state is easier to measure, and that is why it is important in our calculations, and you will see that this is what we use mostly. So, Nc at steady state would be Nrt Cl naught Kd plus Cl naught, clear. So, that is what we do when we plot in the do a scattered plot. So, this is what we start with. So, this is the NC max, this is what we call NC max. Why? Because that is a maximum, as you can see over the from the plot over here, that is a maximum value of NC that is attainable. So, the maximum value is attained at steady state. So, we call this NC max, and that is given as nRT Cl naught over Kd plus Cl naught. This I can rearrange, dividing the both sides by Cl naught, I can rearrange this as NC max over Cl naught equals nRT over Kd minus NC max over Kd, and this I can plot because easily, because I can measure NC max. So, I can, what I do is I vary my Cl naught, that is the ligand concentration, I use different ligand concentrations, let it happen for as long as it happens, then take the steady state, measure my NC max. How do I measure? Because I told you the other day that we label these ligands. So, we label ligands will limit fluorescence or something, some kind of labeling. If it is a fluorescent labeling, then we can measure the complexes straight away. So, at steady state we measure how much complexes have been formed, and we plot this NC over Cl naught versus NC, we plot this, and then we can get the rate constants Kd as well as nRT, fine, from the slope and the intercept. So, the slope will give you minus 1 over Kd, the intercept will give you nRT over Kd. So, you can evaluate both nRT and Kd, fine. This is known as a scattered plot, and it is a very important plot because we will keep referring to this. What I want to mention to you that scattered plots can come in different ways. I think I gave you an assignment also where you had to plot the scattered plot. So, scattered plot can come in various ways. The only thing that is common or unifying between these different ways as the scattered plot appears is the fact that these are steady state plots of complex versus ligand in some form. So, you can keep varying the form of the scattered plot, but it still remains a scattered plot, as long as the complex versus the ligand is in one axis, you have the complex, and the other axis you have the ligand, fine. So, this is I think the problem that I gave you, and I hope you did that. So, today we start something. So, this was all these analysis that we did was for the case where we assumed a simple reaction kinetics R plus L giving a complex, and we assume that it is a second order in the forward direction or first order in the backward direction. Now, that may not be the case all the time. So, that is what we are going to look at. So, as you see on the screen, what this is called deviations from biomolecular kinetics. So, what we had looked at till now is biomolecular kinetics. Okay. So, deviations from simple biomolecular kinetics. So, R plus L giving C is a biomolecular kinetics, and this is, if I am doing a scattered plot, again this is a scattered plot. So, NC over Cl naught versus NC, okay, right. So, this is scattered plot, and the scattered plot is something like linear, just as we plotted it here, right. This is a linear scattered plot because NC over Cl naught versus NC. So, this line in the middle that you see corresponds to the biomolecular kinetics, okay. Now, this line below is this curved line, and the line above this corresponds to deviation from the biomolecular kinetics, okay. So, it does not have to be necessarily biomolecular, and what we will do in today's lecture, we will study that why does it not have to be necessarily biomolecular. If it is not biomolecular, what are the options, how does it react, and try and understand this, and this is known as cooperativity, okay. Positive cooperativity and negative cooperativity, and in earlier course we had studied this, if you remember, that oxygen plus hemoglobin, so this was a reaction that we studied, oxygen plus hemoglobin is HbO2, right, in one of the earlier cases, and what we figured is that one can assume it to be 4O2 plus Hb4 because hemoglobin comes as a molecule of 4 Hb4O8, okay, K1 K minus 1. So, this is a very important physiological reaction, as you all know, the reaction between oxygen and hemoglobin, and that is how oxygen is carried into our blood through oxyhemoglobin, and this is the formation of the oxyhemoglobin. So, this is what is written standard, okay. This is a variation on that. This is a variation on that. So, this is a standard bimolecular form, this is standard bimolecular form. So, this is assumed that one molecule of oxygen reacts with one molecule of hemoglobin, that was the assumption. But then later it was found out that these hemoglobin molecules remain in cluster of 4, Okay. So, therefore, one molecule of oxygen cannot react with a cluster of 4, it has to be 4 molecules of oxygen reacting with a cluster of 4. Okay. So, the bimolecular form is no longer preserved over here. So, it is one molecule of hemoglobin reacting with 4 molecules of oxygen essentially. But in reality, this is also a hypothesis. In reality, what happens is that when you write the oxygen hemoglobin equation, you find that if I am to write it in a certain way, say for example SO2, that is the saturation of oxygen, it turns out it goes as O2 to the power n divided by plus O2 to the power n, something like this. Okay. So, where n equals 2.1 or 2.3 or 2.34, something like that, which means that it is neither 4 molecules nor 1 molecule, but some fractional molecule reacting with hemoglobin. Which, what does it mean? What does it imply? Is it that the fractional molecule 2.34 molecules of oxygen are reacting with hemoglobin? Of course not. What it means is that there is cooperativity between the molecules. Okay. Cooperativity means that the affinity towards, so first say for example, so you have the hemoglobin which consists of four molecules, and you have together cluster of it, and you have one oxygen combining with the first hemoglobin molecule. What follows is, after that there is a certain change of affinity of the process of the system, which means that the second oxygen molecule may not be attracted towards the second hemoglobin molecule as much as the first one was. Okay, or maybe more attracted, whatever is the case. In most cases it is less attracted or more attracted, whatever is the case. But the point I am trying to make over here is that there is a change in the affinity. So, the first molecule reacts as if it is simple bimolecular. The second molecule, in the presence of the first reaction having occurred, does not react any further as if it is simple bimolecular. There is an alteration in the thermodynamics of the process, there is an alteration in the basic, which leads to an alteration in the basic kinetics of the process. Okay. So, this is known as cooperativity, that having one of them having reacted in the vicinity, if you want to have the second reaction may be more favored or less favored. Okay. And from that you come up with the concept of the positive cooperativity or negative cooperativity. Positive cooperativity means there is a positive, that is a more favored effect. So, positive cooperation between the groups of molecules. So, the presence of the first group for the first complex actually facilitates the formation of the second complex. Negative cooperativity means that the presence of the first complex actually retards the formation of the second complex. So, this is the concept of cooperativity. Is it clear? I think for many of you it might be a new concept, but the fact of the matter I am trying to trying to convey over here is simple. It is that you have, for most cases we assume a simple bimolecular kinetics, but when clusters of molecule react with each other, then simple bimolecular kinetics is no longer preserved, not necessarily preserved. You can have the first reaction, the first set of reactions favoring or hindering the second reaction. Similarly, once two reactions have occurred, for example, in the case of hemoglobin, once two reactions have occurred, the third set of reaction may be favored or hindered. Okay. So, depending on that you can have positive cooperativity or negative cooperativity. And if I go back to the screen now, you will see that this is the case, the central line in the middle, this is a Scatcherd plot again, NC over CL naught versus NC. This is a case where there is just normal bimolecular, BM represents bimolecular, okay, reversible REV BM binding, reversible bimolecular binding. So, this is the case where simple bimolecular binding is there. This is the case where positive cooperativity is there. Okay. KD is a dissociation rate constant. So, if I go, it's I think K minus 1, let us see, I think K minus 1 over K1 is a dissociation rate constant. The dissociate, not the rate constant, equilibrium rate, dissociation equilibrium constant. So, positive cooperativity, as I showed you for the case of hemoglobin, is, what did I say, that positive cooperativity means that the second reaction is more favored than the first reaction, the third reaction is more favored than the second, and so on. So, for earlier formations actually favor the latter ones, fine, which means that the KD apparent, the dissociation rate constant, apparent dissociation rate constant is less than the bimolecular rate, rate constant. Is that clear? Because if the dissociation is what? Backward over forward. So, if the backward rate constant is actually lower than the previous case, then it means that dissociation is less favored and association is favored, that is formation is favored, binding is favored. So, this reaction oxygen plus hemoglobin over here is pushed in the forward direction more for the second case. For the third case, it would be even more pushed in the even more forward direction. So, I gave you this example of hemoglobin to explain this, how these 4 molecules bind one after another. Is that clear? So, that is a concept of positive cooperativity. So, positive cooperativity means that the dissociation rate constant, apparent dissociation rate constant is less than the bimolecular dissociation rate constant. Similarly, you can have negative cooperativity, and we will have examples here itself, where the apparent dissociation rate constant is greater than the bimolecular rate constant, which, or in other words, it means that the dissociation is being favored, dissociation is being favored, association is being less favored, right. Okay. So, this is what we have, the negative cooperativity. So, what we want to study is that as I said, that what we did in the last class was a simplistic case, okay, a simplistic case of simple biomolecular kinetics. And if you have a simple biomolecular kinetics, as I showed, that the slope of this is simply going to be minus 1 over kd, okay, and the intercept is going to be nRT over kd, and you can evaluate kd of an nRT. But if it's positive cooperativity or negative cooperativity, then what happens? These slopes these are convex or concave in shape, and then you cannot make such simplistic or straightforward calculations from the slope. So, you have difficulty in figuring out what the apparent, even the apparent the kd apparent that you have is. So, what we will try to understand is how these, what is the real chemistry behind these question of cooperativity, how does it happen, and try and understand and quantify these cases. So, we will look at each of these cases slowly. So, the first case is ligand depletion, and I already talked about this in the previous class. What did we talk about in the ligand depletion case was that you assume that the ligand is present enough, yeah, that is present in excess, but that is not necessarily true. The ligand is obviously going to be depleted unless you have a lot of ligands. So, in real cases the ligand depletion can occur. So, that is case A. So, that can lead to these kind of deviations from simple biomolecular kinetics, right. The second possibility is that the multiple receptor populations of different affinity, okay. So, which means that the same ligand can bind to multiple receptors. You can have two kinds of receptors, two populations of receptors R1 and R2, and the same ligand can bind to these multiple receptors. So, in which case there is obviously a deviation from the simple bimolecular, still might be bimolecular, but each of these might be bimolecular, but the simple one ligand one receptor bimolecular kinetics is no longer there. Okay. The third case is multivalent ligand binding, which means that earlier we had one ligand binding to one receptor, one ligand molecule. You can have more than one ligand molecule binding to one receptor molecule. So, that is the third possibility, and the fourth possibility is receptor aggregation. So, in receptor aggregation what you have is receptors themselves can aggregate and form a complex before they bind with the ligand. So, receptors may form complex with each other before binding to the ligand. So, as you see over here, an example is given. So, two receptors R and R, they bind to form RR, and then they react with the ligand L to form LRR, and then they again react to find with the another ligand L to form LRRL. Okay. So, this is exactly similar to the hemoglobin thing, So, hemoglobin, what happens essentially, if I can write this for you, if I have to do this four of them. So, this is how it happens. Okay. Hb4O2, then Hb4O2 reacts with O2 again. Okay, this is exactly that thing. So, it is like a ligand aggregation thing or receptor aggregation thing. If O4, then Hb4 O4 plus O2. Okay. So, this is how it happens. So, you have the, so let us say this is a receptor for your case. So, you have 4 of those receptors aggregated together. Okay. So, if you go back to the screen, so this is what you have. So, these receptors have aggregated, and it does not have to be 2. I gave you an example of 2, it could be 3 receptors, 4 receptors. Here for hemoglobin you can imagine the 4 receptors being aggregated. So, 4 receptors may be aggregated, and the ligand will come one by one and bind, and finally you will still have the one receptor for one ligand. Okay. So, you will have RNLN, that kind of molecule. So, the molecule formed over here is RNLN, where n equals 2, but you can have n equals 3, 4 and so on. But the point that I am trying to make is that when you have these kinds, so in terms of molar ratio you can still have the 1:1 ratio of RNL in the final thing, but the kinetics changes. Whenever you do something like this kind of aggregation occurs, the kinetics is no longer simple biomolecular kinetics. So, that is the thing that I am trying to convey over here. Okay. So, let us look. So, what we will do is you had these 4 different cases. So, I will try to look one by one at all the cases, and I might leave out some and which might give an assignment. So, the first case I gave was talked about was the ligand depletion. So, let us assume that ligand depletion does not occur, does occur. So, we had initially assumed that ligand depletion does not occur. How did it help us not assuming that ligand depletion occurs? Reduce the order of kinetics from second order to first order, and it was easier for us to solve. Now, what will happen? It is very straightforward. We will simply have a second order kinetics. So, if I go back to the screen, so my earlier assumption was that Cl equals Cl naught, because this term was very valid, very small, and this is no longer valid. So, what I do over here is, let us go back to the equation, otherwise you will not remember. Here, sorry, here this is my equation after I had converted all the concentration into numbers. So, this is the equation I have. So, what I want to do to this equation, and I want you to do this on your copies, maybe you write down this equation, and unless you do this quick, you will not be able to follow what I am trying to say. So, write this equation for ddt of Nc equals K1 nRT minus Nc times Cl naught minus n over Na Nc minus K minus 1 Nc. Done? So, so this becomes a second order if Cl naught, if I do not make any assumption, but before that I want to make want you to make this dimensionless, and this is something that we will need later. So, now I want to make this dimensionless using these dimensionless groups, which is u equals Nc over nRT, tau equals K inverse T, K minus 1 T, okay. K minus 1 is first order rate constant. So, tau is dimensionless, eta is nRT over NaC n nRT over NaCl naught. Okay. Why n nRT over Na? Because that has the units of concentration, right. N nRT, n is number of receptors per unit, sorry, nRT is number of receptors per unit cell, n is number of cells per unit volume. So, n times nRT would be number of receptors per unit volume, that divided by Avogadro number would be molar, okay, molar concentration. So, that you divide by Cl naught, it is dimensionless, and alpha is Cl naught over Kd. Okay. Is that dimensionless? Cl naught over Kd? Yes, that is, because Kd has K is K minus 1 over K1, K minus 1 has units of inverse time, and K1 has units of inverse concentration inverse time. So, Kd has units of concentration, fine. So, what do you get if you put that, if you so what I want you to do now is put these dimensionless constants into your equation, the equation 4 that you wrote. So, the equation 4 was so then u equals CL naught over KD. So this is nRT del U del tau nRT over K minus 1 equals K1 nRT 1 minus U and CL naught minus K minus 1 times nRT times U. Then should be a alpha CL naught KD. Then if I cancel nRT K minus 1 all through the equation, then you will get del U del tau equals 1 minus U to alpha K alpha will come in the outside here. Let me check just. So you have K1 nRT. Is this what? Is this right, or is there some term missing here? Which one? This one? This side? Into K minus 1. Okay, yeah, that's why it will come in the denominator then, and then you will have KD over here from that, yeah. Into K minus 1. And this is correct, right? Alpha D over this. So basically what I have to do is, I have to actually it might be better to just keep this as CL naught instead of alpha D and then divide the whole thing by CL naught. Yeah. So then I think you will get alpha, yeah, because so you divide the whole equation, everything by both sides by K minus 1 nRT K minus 1 nRT. So this side it will cancel out, you will get K minus 1 nRT over here. So let me do that. So you will have del U del tau equals K1 over K minus 1, which is 1 over KD, right, into 1 minus U, and this is CL naught minus N nRT. CL naught I can take out, so this will have 1 minus eta times U, right, minus U, fine. So and this will give me alpha. So this is 1 minus U times 1 minus eta U times alpha minus U, right. So then you will have, okay. So this is a basic equation and I now need to solve. So what is going to be my initial boundary conditions and so on, initial or boundary conditions, whatever it is. So my initial condition earlier was that NC equals NC naught at t equals 0. So now if I put back into my dimensionless variables, I will have U equals U naught, okay, equals NC naught over nRT at t equals 0, fine. So this is my equation that I now need to integrate, okay. So these are, if you need the steps, these are the steps. So, these are the steps, and so this is what I got, and this is what I need to integrate now. Okay, so how to do that? We discussed this already in the last class. You can use partial fractions and integrate it, and because it's a second order and it's already in the form, you can break this up and get one full partial fractions in u, and then it will be 2 exponentials, fine, and we will do that in a minute. Before we do that, we are going to do something a little clever, which is the steady state solution of this. So, this thing that you have over here, we will look at the steady state. So, the steady state is simply 1 minus eta u alpha equals u, okay, steady state. Fine. So, why are we looking at the steady state? So that we can do the sketched plot. Okay. So, let us now go to the screen. Yeah. So, what we have over here is a sketched plot. So, this is u over alpha equals 1 minus u times 1 minus eta u is a sketched plot, and this is how it varies. So, as you can see over here, what we have here is that two variables are here. So, one is alpha and the other one is eta, okay, two parameters, sorry, u is a variable and we have two parameters in the system. So, earlier we had how many parameters we had? We had plenty of parameters actually. We had the forward rate constant, backward rate constant, n, nRT, Na, Cl naught, plenty of parameters. So, 6 parameters we had. What we had been able to do through these dimensionless numbers and groups over here is that we have been able to reduce the number of unknown parameters from 6 to 2, because it is always hard to be able to evaluate these unknown parameters, and now we have been able to reduce them from 6 to 2. Now, let us look at this expression carefully. Q over alpha equals 1 minus u times 1 minus eta u, or this expression, one of these steady state plots. Now, what is alpha? Alpha is so this is, as I told you just a little while back, that this is sketched plot, and there is no need that to assume that sketched plot is simply going to be NC over Cl naught versus Cl naught. All steady state plots that involve the complex concentration and the Cl naught, that is the ligand concentration and the complex concentration, are sketched plots. So, this is also a sketched plot, and there is no need to presume that sketched plots are only going to be NC over Cl naught versus Cl naught. So, if you look at this plot, what is u over alpha? Look at the dimensionless variables given on the screen. So, u over alpha is NC over Cl naught times Kd over nRT, right. So, it is essentially again NC over Cl naught. So, the original sketched plot had NC over Cl naught versus NC. So, this is also NC over Cl naught times some parameter, and what is u? U is NC over nRT. So, simply it is the same kind of thing. Now, what is eta? Well, that is something we have to pay a little attention to. Eta is n nRT over Na over Cl naught. Okay. So, what does this eta signify to you? Just look at the screen and tell me. What does this eta signify to you? The answer is right there in front of you on the screen. So, you just have to look and tell me. So, just look at these plots over here for different values of eta. What does it signify? About what?
Concentration of ligand.
Yes. So, essentially look at eta. Eta is nRT Na over Cl naught. So, nRT Na, n nRT Na over Na is fine. Denominator you have Cl naught, which means that if Cl naught is very large, if the ligand concentration is very large, eta decreases and it goes to 0. So, you see over here, that is why I purposely drew this, that for eta going to 0.01, it goes back, it collapses to the linear first order kinetics, and for eta larger and larger, more is the deviation from the first order kinetics. That is all I wanted to say over here. That is the reason I drew this sketched plot, is I just wanted to convey the fact that if you go away from eta equals 0, your deviation from the simple linear kinetics is more, and you have this kind of things. So, that is the sketched plot. Now, can we this model that we have over here, yes, here, sorry, this model that we have over here, can we integrate it in time? Of course we can, as I said, through partial fractions, and we can get the temporal variation also. We are always more interested in steady state concentrations or scattered plots. The reason I just mentioned is because they are easier to quantify. Experimentally, scattered plots are easy to draw because you can just leave the system for as long as you want, and let it let the experiments happen for 4 hours, 6 hours, 8 hours, 10 hours, and at the end of which you can go and collect. Whereas if you want to do a dynamic study, you have to collect at every time point, every 30 minutes or 20 minutes you have to collect, and it makes it difficult. So, this, but again we can always do that. So, again this is the solution of the unsteady state model, and what I have done over here is this is a case for eta equals 0, okay, which means that simple linear kinetics, and these are the deviations from that, and as you see that as you keep increasing eta, the deviation keeps increasing more and more, and also the deviations depend on alpha 2. But here I think this is a small typo over here. Errors are the errors means basically deviation. These are not errors, these are deviations. As you look on the screen at the bottom of the screen here, I think this is typo. So, for eta equals 0.1, the error is 1%, and eta equals 0.1, no, I think it is sorry, the typo is eta equals 0.01, the deviation is 1%, and for eta equals 0.1, the deviation is around 3%. Okay. So, these numbers, and then as you keep increasing your eta, you can see that there is a huge difference. This is almost what 40% difference, and this is error is around 40%, not error, is essentially these are differences. So, this 40% and this could be around 70% or so. So, so what this is trying to show is that the near eta equals 0. So, this I am sorry, this one eta should be eta equals 0.01. So, for that the deviation is 1%, for eta equals 1 the deviation is 3%. Okay. So, the next case we look at, so if you go back and look at 4 different cases, was first one is ligand depletion, second was multiple receptor, and third one is multivalent ligand. So, the next case that we look at is the multiple receptor, 2 or more receptor populations. Now, what does the intuition tell you? So, the first case we did was very straightforward, where we had the equation and the model, and all we needed to do is fiddle around with the CL term, but this we do not have a model for multiple receptors. Okay. So, if I have to ask you to write a model, so what does your intuition tell you? How do you write a model for multiple receptors? You have one set of ligands, but let us say 2 sets of receptors. How do you do that? One possibility, and the simplest possibility, is that the receptors would not interfere with each other while they bind, okay, which means that receptor 1 binds independently to ligand and receptor 2 binds independently to ligand. That is a possibility. So, this is a possibility that we explore over here, where receptor 1 and receptor 2 bind independently to each other. Now, if they bind independently, how do you model it? The model is still not there on the screen. So, how do you model it? So, let us go back to the old model, and then you can tell me how you are going to model it. This was the old model I had, right. Now, I tell you that very clearly that the receptors do not interfere with each other. So, what will happen? So, you will have these 2 sets of reactions, L plus R1 giving C1 and L plus R2 giving C2, right. So, dC1 dt would equal, let us say this is K1 1 and K1 minus 1 and K2 1 and K2 minus 1. Right. So, then this will be my K11 CLCR minus K minus 11 C1, and dC2 dt would be K 21 CL CR2 minus K minus 1 to C2. Okay. Now, if the receptors, so from these set of systems, are these two interdependent on each other? This is a question you have to answer A, and under what circumstances they are not really interdependent? B. Two questions. Are these two equations that I wrote in the curly brackets here, are they dependent on each other? Yes, they are, because through Cl. What conditions are they not interdependent? Large. If there is no ligand depletion, if ligand is in excess, then Cl, each of these Cl, you can write it as Cl naught over here. So, for Cl not very large, replace Cl by Cl naught. Right. So, you can replace Cl by Cl naught, and then what happens is these two systems become decoupled. So, typically the ligand concentration is more or less large. If it is not large, then what are you supposed to do? You are supposed to solve these two coupled equations together, the two coupled equations that you have here. You have to solve these two together. Okay, that is the possibility. I am going to give you a question like that. But if the ligand is large enough, then you can decouple them, you can solve them separately, and what will happen? You will get the same solution for each of them, right. So, the maximum NC max that you got previously dependent only on one ligand concentration and one receptor concentration. Now, there are going to be two of them, and you can add them up, right. If these two are completely independent, what you see over here is not complete independence, but if the ligand concentration is very large, then they become completely independent. You allow each of them to react in their own way, get the steady state value, and you add them up. Okay, that is a possibility, but that is not always a possibility. That is one of the possibilities that can happen. Okay. So, this is a case where each receptor acts independently. So, as you see on the screen, the first part Cl naught. So, this is a case where everything is Cl naught. Okay. So, there is no ligand depletion at all, and Cl naught nRT1 over Cl naught plus Kd1, that is the first one, and then Cl naught nRT2 over Cl naught plus Kd2. Now, I tell you one thing, I give you an assignment, you can do it and submit it. You are supposed to submit one assignment today. No, whatever you submit the assignment, whatever you did is submit the assignment, and I give you this assignment for next week. I'll probably add in another problem tomorrow. So, this assignment is a case where we consider two or more receptor populations. Previous case, what did we assume? Ligand depletion. In this case, what we have done here, there is no ligand depletion. What I want you to do is couple these two cases A and B, that is ligand depletion plus two or more receptor populations, fine, and then get the model for that and the solution and come up with the steady state. Is that clear? Right? You can write all of you down this. So, first case we did was ligand depletion. Second case we are doing now is two or more receptor population. I want you to couple these two and come up with the model. I already wrote, but solution of the model essentially, and the steady state value of two or more receptors in the presence of ligand depletion. Clear? So, then the receptors cannot act completely independently like it does over here. Fine. So, even here when you have a steady state solution, steady state solution, a steady state value for this, as you see given on the screen, what happens? You are doing this whole experiment in a beaker with one set of receptor, and let us say two sets of receptors and one set of ligand. Okay. At the end, what you probably have, how do you measure? How do you measure? I mentioned this by labeling the ligands, right? You label the ligands with some sort of fluorescence or something, and once the complex is formed, you have the labeled complex, right. So, you have one set of ligands and two sets of receptors, and you have labeled your ligands, for example. Now, the complex is formed, you can get the total amount of complex that is formed at steady state, right, but it is going to be very hard to be able to separate out the kinetics of these two. Why is that? Because what you will see at the end of the day is a labeled ligand. Now, there is a way, when you draw the scattered plot, you may be able to separate out these two, the kinetics of these two reactions, that is reaction of ligand with receptor 1 as against reaction of ligand with receptor 2, you may be able to separate it out through scattered plot, but only in the case when these two are very dissimilar, or the kinetics of these two are very dissimilar. What I mean by dissimilar is that, for example, one of them, for example, is very slow, the kinetics of one of them is very slow as compared to the other, then only can you separate them out, and we will look at this right now. So, is as I said on the screen, that it may not be possible to distinguish between the two kinetic constants, dissociation constants here, unless they are very different from each other, and by very different, at least by one order of magnitude. So, one has to be 10 times larger than the other at least. Okay. So, this is a thing, you know, with the assumption that this is not what you are supposed to write the model, but this is a model with the assumption that ligand depletion does not occur. So, then these two equations become independent to each other, and you can solve them, and this is the solution you get. Okay. So, this is, I want you to get same kind of solution, but with these two coupled systems, and yeah. So, yeah, I think these will be second order coupled equations. So, you probably have to use, what do you think, would you be able to solve this analytically with the equation that if I can go to this page over here, this thing that I gave you, this these two equations, do you think you can solve it analytically? Here we could solve it analytically, the one that we did, but do you think these two we'd be able to solve analytically? Just as a hint, you know, to help you with the process. Do you think you can solve this analytically, or numerically? Of course, you can solve. Okay, second order system, but what about analytically? Can you solve this? Once you have to go back and put your Na and all that stuff, you know, and convert this into numbers like we did all the process. But after that, what? If it is a single second order equation, you can solve it analytically. Now, I have coupled the system, then what? I showed you last the single ligand depletion case. Can you not? Anyway, let us not debate over that, you do that as an assignment, but for this case where ligand depletion does not occur, you can get an analytical solution. So, each of them becomes like what we got before, and this is an analytical solution. Remember, the initial condition is given as NC1 equals 0 and NC2 equals 0. So, that any other term that was there drop out, and you have these two. Now, but what I was trying to tell you is, experimentally you cannot separate out NC1 from NC2, right? Is it clear? When you are measuring, you can only measure NC, because you will be able to get the label ligand. Now, how do you separate these two rate constants then? If you can only measure NC, and then what is the way to separate out these two rate constants? The way would be to look at the slopes, and we will do that in the next few minutes. So, look at the slopes and look at if there are differences in the slopes, and what you will find is that if one of those dissociation constants is 10 times the other, then there are differences in the slopes. So, this is how it looks like, and the diagram that you see on the screen. So, this is the dynamics of the process. So, this is this equation, the final model that I wrote over here, that one solved. So, this is a case of a single receptor. Okay, this is the old solution solved, sorry, this one solved. Okay. And this one is the last one, the 2 1 solved. So, as you can see over here, that with 2 receptor model, what we have done over here is KD, we have taken a system where there is a large difference in the dissociation constants. We have purposely taken this where there is a 2 orders of magnitude difference. So, one is 100 times the other. As a result, what happens? You see a very distinct slope, difference in slope. Okay. Can you explain why this is happening? And this curve, the x axis is time. The y axis is the total amount of complex that is being formed, and x axis is time. Now, you have to tell me, so given the values, the KD1 and KD2 values are given, so you have to tell me that what is happening. Maybe we will go back to the screen and look at the screen here. So, what is happening over here? You know, these two slopes, being very different? Why are these two slopes very different, and what can you infer from the difference of slopes? KD1 is KD2 is 100 times KD1. What does it mean? Not that complicated. Which one? You have to tell me specifically, not one of the terms. KD2 is dissociation rate constant, okay. So if KD2 is higher, which means what? KD2 is higher, much higher than KD1, which means out of receptor 1 and 2, what is the process? What is really happening here? Let's look at the curve, because it's important to look at the curve, but from the curve let's try and understand what is happening, what's the process that's happening here. So KD2 is much higher than KD1. KD2 is what? K2, K minus 1, let's say 2 over K1, and KD1 is K minus 1, 1 over K1, right. So if KD2 is much higher than KD1, it implies that K1 2, let us call this, and K1 1. So one possibility is that K1 2 is much lesser than K1 1, or K minus 1 2 is much greater than K minus 1 1. Okay. Whichever way, what does it imply? That what does it imply here? That the second, if second association rate constant for the second is much lower than the first. So as soon as you put the whole stuff in there, into your beaker, the receptors are there, and you put your ligands in there, what starts to happen is that receptor 1 starts to react. Receptor 1 starts to react with the ligand, okay. And then if there is a large difference in magnitude, so receptor 2 hardly reacts with the ligand, okay. So receptor 1 starts to react dynamically. This is what happens. Receptor 1 starts to react with the ligand, and then it saturates out. So all the receptor 1 that are there are being combined or reacting with the ligand. They are being taken up, and complexes are being formed till a point where no more receptor 1 is available. Is it clear? So till a point where no more receptor 1 is available, and then the receptor 2 starts to react with receptor 1 with ligand. Okay. So if there is a 100 to 1 ratio, then if I go to the screen, then we will see if there is a 100 to 1 ratio, then what happens when this is reacting, for the first receptor 1 is reacting. So 99% of the receptors that are reacting are receptor 1, only 1% are receptor 2, and that continues more or less till steady state is reached. So this time over here, whatever the time is, let us say 0.15 minutes or something, 0.1 minute, whatever the time is a time when the first process, that is receptor 1 combining with the ligand, has more or less reached a steady state, and then the second process starts. Okay. So ideally what would happen is, if there is a one receptor, only receptor 1 would be there, this will saturate out over here, flatten out over here, but that does not happen because there is a second receptor standing there, and that starts to react and form this. So this difference in the slope can help you figure out what the constants are, and as you can see over here, look at these numbers. nRT1 over NC max is 0.3 and nRT2 over NC max is 0.7. Okay. This is very intuitive. The reason being that nRT1 plus NC max is what? The maximum number of complex that can be formed. The maximum number of complex equals the total number of receptors that are there. If there are no other resistances in the system, the total number of receptor 1 at the limit, at best, what can happen is total number of receptor, all the receptor 1 can react, okay, which it does, and also all the receptor 2 can also react, which may or may not happen, but all receptor 1 will definitely react. So if that happens, then NC max will be nRT1 plus nRT2. As a result, nRT1 over NC max is 0.3 and this is 0.7, and the summation of these two would be 1, or in other words, NC max would be nRT1 plus nRT2. So, the total number, maximum number of receptor complexes that can be formed is the sum total of the two kinds of receptors. Okay. Now, the last thing we will do today is look at this scattered plot over here. Sorry, not the scattered plot, this is still the unsteady state plot, but this is done in terms of 1 minus NC over NC max. Okay. Why 1 minus NC over NC max? Because if you look over here, this there is this terms over here, this constant terms over here, and if you do the 1 minus NC max, and what will happen is that you will get the exponential parts and you can take the log of that. So, it is the same kind of variation as you see, exactly the same thing, it is only that the plot has reversed itself because it is in the log scale and minus and all that. So, you have two varying slopes, and from these two varying slopes you could be able to separate this thing out. Now, what I want you to do is quickly again we have a class, one more class today, but write down this problem for now. And this would be a second problem for assignment. Show by rearranging the equation NC equals CL naught nRT1 over CL naught plus KD1 plus CL naught nRT2 over CL naught plus KD2. So, this is essentially NC max 1 plus NC max 2. Okay. Show that by rearranging this equation you can determine the 4 parameters nRT1, nRT2, KD1, KD2 for 2 receptor populations from the scattered plot. Assume that one of them is much, so you can assume one to be 100 times higher than the other. So, what I did, I showed you the scattered plot, and all I am trying to tell you is that how can you exploit this steady state equation that is there to get, how can we exploit this to get the 4 parameters nRT1, nRT2, KD1 and KD2. Okay. So, we will stop here and we will continue later today.